Thank you for the invitation. So the title of my presentation is The Turbulent Lives of Young Galaxies. So the first half of my talk is going to look like a galaxy formation talk. I'll talk about predictions for the properties of high redshift galaxies. And in the second part, I will develop the connection to turbulence, to the physical state of the gas in these high redshift galaxies. I've done this work with a number of collaborators on the slide here, and I want to highlight in particular those in the first row who led the papers, which I will highlight today. So Jason Soon is currently a postdoc at Northwestern. Alex Kervish is a recent PhD student. Jonathan Stern is now a faculty member at Tel Aviv, and Zheng Shegma did a lot of the early work on these high redshift predictions. So these predictions are from cosmological hydrodynamical simulations from the FIRE project. So these are zoom-in simulations which have sufficient resolution to resolve some of the main structures in the interstellar medium of individual galaxies, while at the same time capturing the cosmological environment. And what the video here shows is the formation of a galaxy which by redshift of 0 has a mass comparable to the Milky Way. The top panel is gas, color-coded by temperature, and the bottom panel is where the stars are forming. And you can see that at high redshift, the gas is highly clumpy and also highly dynamic. And it's only at relatively late times, starting at about redshift of 0.8 in this particular simulation, that you will see the emergence of a long-lived, rotationally supported gas disk, starting about now, out of which gradually stars will continue to form, and by Z of 0 produce a pretty reasonable disk galaxy. So this is just one example, but we have dozens of simulations like this one now, and this phenomenology is representative of what we predict for the evolution of galaxies at that mass scale. In particular, a long-lived thin disk only forms at late times, or when the galaxy becomes sufficiently massive, which is in contrast to what you saw at high redshift when the galaxy had a low mass at times when it was repeatedly blowing itself apart by bursty stellar feedback. Now, in that presentation, I will often talk about the phenomenology of high redshift galaxies, but here I want to emphasize that this phenomenology not only applies to high redshift galaxies, but it also persists in low mass galaxies down to low redshift. But for kind of conciseness, I will talk about high redshift galaxies. Okay, a little bit more quantitatively, at the top left panel here shows in black the star formation rate in that simulated galaxy in the high redshift regime, from redshift of 4.5 to redshift of 2. And you see these very large spikes, which indicate that most of the stars are forming in a relatively small number of very intense bursts. And typically, each burst of star formation is followed in red by a spike which traces the rate at which gas is outflowing through the circumgalactic medium. So this traces galactic winds that are powered primarily by supernovae that explode a few million years after a burst of star formation. And that corresponds to times where the cool gas in particular is highly clumpy and highly dynamic. And what I find somewhat remarkable is that the same simulated galaxy, by redshift of 0, has settled into a state in which the star formation rate is nearly constant. Its outflows are much weaker. They're more like galactic fountains at the disk halo boundary. And those times correspond to much more ordered gas configurations. In this case, a thin disk plotted face on. So next are Mark Hubble Space Telescope images of fire galaxies at redshift of 0. This is primarily to give you a visual sense of the level of detail in these cosmological simulations. So most of these are star-forming disks plotted face on, you can see dust lanes that attenuate the blue light from young stars. And one of those galaxies was rendered edge on, so you could see how, in spite of the high redshift bursty state, this galaxy formed a nice thin stellar disk by redshift of 0. Contrast these Mach Hubble space telescope images with predictions for JWST at redshift of 10, which implied much more clumpy and disturbed morphology. So this particular filter rests optical. These were predictions published in 2018 by Jean Schregman, so more than 5 years ago. So true predictions for the purpose of JWST observations. And so more recently, in papers that Jason Sun led, we reanalyzed the same simulations, and we compared them with new JWST data. So these results are for the rest UV luminosity function from redshift of 8 to redshift of 12. The solid maroon curves are what we predict from the fire zoom-ins. And the data points are JWST observations in the last couple of years. The open data points are from photometric catalogs, so these are not guaranteed to be pure. And in contrast, the solid data points are from spectroscopic measurements. So these are strictly lower limits to the UV luminosity function. But in any case, what you can see is that our predictions go pretty much straight through the very high redshifts. And in particular, we did not need to change the cosmology, assume a non-standard IMF, or assume that, say, AGN contributes to the rest UV light that is observed. Obviously, that is not to say that these things are ruled out. They remain interesting to investigate, but they do not appear to be necessary to explain the abundance of galaxies in the rest UV at these redshifts, including at the high luminosity end. This is in contrast to many studies that you may have heard about, maybe in the New York Times, which found that most simulations underpredicted the number of high luminosity galaxies that JWST discovered. And I think that one of the reasons for this is that most of those simulations had relatively coarse resolution in the ISM, and some of these models were semianalytic, used a semianalytic methodology. So in particular, they did not predict the kind of bursty star formation that comes out naturally out of the fire simulations. And in this paper, Jason showed that the burstiness that we find in fire is crucial to explaining the bright end of the UV luminosity function at this very high redshift. And the reason is that the rest UV, it traces the recent star formation. So if your star formation rate is highly variable, so is your rest UV luminosity going to be. And what this variability does is that it scatters into high luminosity bands, galaxies, and these are bands which would otherwise contain very few galaxies, because the stellar mass function tends to be exponentially truncated at the high end. And this is why this variability can boost the number of galaxies we observe at the high luminosity end by up to an order of magnitude, which is what we find in this regime. Okay, you can see this because the maroon curve is the same as on the previous slide. So this is the self-consistent UV luminosity function prediction from fire, taking into account the time variability of the star formation rate. And in blue, it's kind of an artificial prediction in which we've artificially smoothed the star formation histories with a time scale of 100 million years. And you can see that would kind of suppress the number of high luminosity galaxies that we would predict. And that would underpredict the observations. Now, this burstiness has some important implications, including for selection effects in galaxy surveys, because it means that the same galaxy, if you could observe it as a function of time, if it's not too much above the detectability threshold of a given survey, it would oscillate in and out of a survey detectability. And so that means that at the fixed stellar mass, some of the galaxies are going to be in the survey and some are not going to be in the survey. And the ones that are going to make it into the survey will have biased properties relative to the underlying populations. For example, with respect to the gas fraction of those galaxies or the specific star formation rate. Okay. So this was kind of the pure galaxy formation part of the talk, and now I want to move on to connect that to the turbulence theme. The next few slides are going to be results from a case study of the evolution of 3 galaxies, which by Z0 have a mass comparable to the Milky Way, from a paper that my former student Alex led. On the right-hand side, we have 2 different metrics of star formation rate variability. So if you focus on the one at the bottom, that's the standard deviation of the log of the star formation rate, average over 300 million years. And the main point here is that this metric of SFR variability drops by about an order of magnitude over a time scale which is cosmologically short, which means that in any one of these simulations, we can identify the time at which bursty star formation ends relatively accurately. And this is a time that we label T bursty, and here these 3 galaxies time and plotted relative to delta T, so T minus T bursty. Okay, and what is now done is plot again the same 3 simulations in these kind of this delta T space and correlate the time at which bursty star formation ends with the emergence of a thin galactic disk. So we have 3 metrics of that. The top panel is a geometric aspect ratio. So values of order unity are kind of quasi-spherical. Small values are disk-like. The middle panel is median JZ over JC, where J is specific angular momentum. So JZ is specific angular momentum aligned with the net angular momentum of the system. And it's normalized by JC, the specific angular momentum if the particle were on a purely circular orbit. So values of 0 for this particular metric indicate disordered motion, and values equal to 1 indicate very nearly circular orbits. And the bottom panel is a more observationally motivated metric of diskiness. So this is V over sigma for the H1 gas. So values of V over sigma of order unity or less correspond to dispersion dominated systems, and high values of V over sigma mean strongly rotationally dominated. And what you can see, if you focus in particular on the gas or the young stars, which are more kind of instantaneous tracers of the dynamical states of the gas in the system, you can see that the emergence of a thin, strongly rotationally supported disk correlates very tightly with the end of bursty star formation. If you look closely, you will see that there is some prior gradual increase of diskiness metrics before T bursty, and this we identify with the formation of a thick disk that you might see, for example, in the late time stellar populations. Now, focusing on one particular example, this is an energy view of what happens to the gas kinematics in a halo, as on the scale of where the stars are located. And so what Alex did is he decomposed the total energy in the gas into 3 orthogonal kinetic components, so radial, vertical, and azimuthal, plus a thermal component. And what he found is that in the bursty phase, you have large fluctuations in that kind of partition of energy, but on average, approximately equal energy in the 4 orthogonal kinetic components and in the thermal energy component. And that changes drastically once you approach once you reach the steady phase, where most of the energy goes into a rotation component. So that traces the emergence of a thin disk. In this next plot, Alex did something similar, but rather than focusing on the inner halo as a function of time, he looked at two particular time slices, so one in the bursty phase and one in the steady phase. And here the horizontal axis is radius in the halo, from the center of the halo to a full virial radius. And what you can see in the top panel in the bursty phase is that kind of in the galaxy at the smaller radii, you have this roughly equal mixture of energy in orthogonal kinetic components and the thermal components. And what is new is that this kind of roughly equal mixture is not limited to the gas within the galaxy, but actually extends all the way to one virial radius. This is an image of the gas at that particular redshift. And this is in contrast to what you find once the galaxy has stopped being bursty. So it's formed a strongly rotationally supported disk in the inner part of the halo, and that disk is now surrounded by a hot circumgalactic medium. And in particular, from that point on, there is a well-defined kind of boundary between the ISM and the CGM. It's kind of where the rotation stops. But that didn't exist prior to the end of bursty star formation. Okay, so the schematic picture is the following. So while the galaxy is still bursty, on the scale of the entire halo, we predict a complex, dynamic, turbulence-like, multi-phase mixture throughout the halo, which becomes a cold rotationally supported disk embedded into a distinct hot CGM after the galaxy has settled into a steady state. Okay, and I want to kind of conclude with some possible theoretical implications of this. So common approaches, including analytic methods, semi-analytic methods, and also idealized simulations, by the way, methods which I have used in some of my own papers, typically assume equilibrium disk conditions to model galaxies. And what the cosmological simulations that I showed today suggest is that these approaches, while they may be very insightful once you have a disk, is long-lived, probably not the most realistic in the bursty phase. And this may have interesting implications for our understanding of how galaxies regulate their star formation or drive galactic winds in the bursty phase. And what I'd like to suggest is that perhaps a turbulence-inspired approach in which star-forming clumps in galaxies corresponds to density peaks in a turbulent flow on a halo scale might be useful to model that bursty state, which would be an analogy to, for example, how turbulence-inspired models have been very fruitful to model the formation of individual stars within GMCs. I'll just leave you with these pictures that show you the multi-phase gas on halo scale in the fire galaxy formation simulation, like the ones I emphasized in my presentation today, compared to what we find on much smaller scales deep into a molecular cloud in which individual stars are forming. It's kind of give you some inspiration about this turbulent approach, which I suggest could be fruitful on larger scales.
Kudos to Claude-Andre for finishing before time. Let's open the floor to questions. Please go ahead.
Thanks for this talk. I was just wondering, in the bursty star-forming ages of this galaxy, do you have enough grid resolution to actually measure a structure function or something inside this region?
We have not attempted to do that. I think it would be pretty marginal.
Okay, so
Yeah,
no.
I mean, so the galaxy is reasonably well defined, resolved in the sense that there's a large number of resolution elements in it, but I think it probably falls short of having enough dynamic range to have a good measurement.
Even in the bursty stage, where the region that is turbulent is much larger than the disk of the galaxy?
I think we could attempt to do that. I don't know.
That would be cool.
Yeah.
Turbulence to me is a cascade. I would like to see it. Be cool.
Let's go ahead.
Nice talk. I'm wondering for the bursty state, is the sonic, like a sonic Mach number much higher than the stable phase? I see the thermal energy is actually quite low.
Could you repeat that question?
Does the sonic Mach number at the
Can you be closer?
Okay. Does the sonic Mach number at the bursty phase much higher than the later phases? Because
solenoidal, is that what you said? Sonic Mach number.
Yep. Because I see the thermal energy is actually much lower than the kinetic energy.
Well, it's very while the kinetic motions can have velocities of in excess of 100 kilometers per second, and some of that gas is 10 to the 4 degrees Kelvin. Yeah, it's 10 to 4 degrees Kelvin, so the eternal sound speed is 15 kilometers per second. So it's definitely highly supersonic.
Thanks.
Go ahead, Jan.
Oh, yeah, this is really beautiful. Thank you. So I'm wondering, do you always see this at high Z only? Or if you look at a low redshift starburst dwarf galaxy, you get the same kind of burstiness? So in other words, is it redshift thing? Or as long as you go to a smaller halo that's accreting a lot of gas, you have this?
Yeah, so I emphasize the high redshift regime. So at high redshift, most of the galaxies are relatively low mass. But redshift does not appear to be the primary variable that determines whether a galaxy is bursty or steady. It seems to be more closely related to the mass of the galaxy. So roughly, galaxies stop being bursty at L star, kind of at the Milky Way mass scale, which is where we find large disks in the local universe. And our low mass dwarfs, they are bursty and fire. So I think a lot of what I presented today would qualitatively also apply to the dwarfs. This is not to say that the quantitative details are the same, right? Because at high redshift, not only are the galaxy low mass, the inflows from the intergalactic medium are much more intense. The dynamical timescales are shorter. So the properties of the burstiness are likely quantitatively different. But that's something that will be interesting to map out more systematically.
So while you're thinking of questions, don't hesitate to come up to the microphones. I have a question. So JWST observations, you have really impressive match with the estimates of masses of stars in the galaxy. What about the black holes? Can you say something about the black holes, their masses?
Can I say something? So so black holes are not included in these simulations. As you know, I guess in my group at Northwestern, we have some papers on black holes and simulations like this. Typically, we focus on lower redshift. I think the black holes in simulations like this one, I view these simulations at present more useful as kind of providing interesting boundary conditions or initial conditions to explore, what happens to the black hole under a given prescription for accretion onto the black hole or a given prescription for the AGN feedback. There are many orders of magnitude of unresolved scales between what's explicitly captured in a simulation like this one and accretion onto the black hole. So we haven't gone very far in terms of comparing the detailed observational predictions for black holes.
Got you. Thank you. Please go ahead.
This might be a naive question, but is there any periodicity to the burstiness, or is it intermittent?
It doesn't appear to be periodic, but it appears to be cyclic. And what I mean by this is that a lot of it appears to be driven by gas in the CGM field, we would call that wind recycling. So you have gas that falls in from the intergalactic medium, fuels the burst of star formation, and then the burst of star formation ejects a lot of the gas back out. But then the gas falls back in.
Mm-hmm.
And so the galaxy appears to be kind of juggling gas in the halo.
Mm.
And so while that doesn't give rise to city, it's also not completely random when the burst of star formation happens. It has to do with these cycles of cool gas to the halo.
Does it matter then where your stars are forming in the disk, like where in the scale height they form to actually get this burstiness in the first place?
Does it matter where the stars form? Not sure I'm going to answer your question directly, but I think this connects to a kind of there's a little bit of a fundamental question, which is that while we find these bursty outflows, that picture is somewhat different than the picture of galactic winds as suggested by many more ideal, I would say many simulations that do not explicitly include the cosmological context. Yeah. So we get in these simulations a lot of cold outflows from low mass galaxies, whereas in a lot of the non-cosmological simulations, it's hot gas that vents out. And to me, it's an open question: what causes this kind of difference in the properties of the galactic wind? And one possibility is that kind of the initial / boundary conditions aren't the same. The system has never settled into a long-lived disk in which we can launch supernovae. And perhaps because it's never reached this like disk-like type of initial conditions, the stars are forming in places in the turbulent flow that's more conducive to launching the cold outflows that we predict then in some of the disk models. So in that sense, maybe there's something that has to do with the locations of star forming regions.
Okay, thanks.
Oh, you kind answered, but partially. So my question is, how do you set? I mean, initially, how do you set the bursty star formation, and what is the period of the frequency or the period? The bursty.
So we don't set it. So what we have is we have gravity, we have radiative hydrodynamics. The gas condenses into dense
but
clumps.
You have to assume some.
And then there's a subgrid prescription for turning the dense gas into stars. Yeah. And kind of the result of the calculation is that it has this bursty character. Yeah. But it was not prescribed to be bursty.
But anyways, you assume some prescription for the supernova induced, I mean, for the star formation rate initially, or not?
There's a prescription for given small-scale gas properties, how fast does it turn into stars? But that's on small scale. So the galaxy integrated star formation rate, there's no explicit assumption about that.
You leave the star formation rate completely as
it's kind of a dynamical variable. It's something that's
and then what is
emerges from the calculation.
What is the frequency of the burst?
That's the prediction of the dynamical calculation.
And the period is, I'm asking.
It's not, as we've just discussed, it's not periodic, but the time spacing between major bursts, I think it's related to the dynamical time scale in the halo, because it has to do with kind of gas clouds being kicked out and falling back.
So you have fountains all the time.
Yeah. So some people call it the juggling mode. You have these flows to the circumgalactic.
Okay.
So I'm curious whether you've tried this at considerably higher resolution, because I think your resolution, your standard fire resolution, is around 10,000 solar masses. So any star formation event will have, many supernovae associated with it, and a number of people, Drummond and we've also shown, and others have shown that, the more correlated star formation is, the more, of course, it's bursty inherently, but also that leads to stronger outflows. So, in this situation, the low mass galaxies are the ones that have a larger ratio of the fraction, the mass of any star formation event compared to the mass of the galaxy, compared to the, depth of the halo potential, et cetera. So have you tried this at much higher resolution?
Yeah, so the dwarf galaxies, we can simulate at much higher mass resolution than the standard 7,000. So we have we have several that are down to about 100 solar masses in resolution, and a couple down to 30 solar masses. And in the low mass galaxies, we always see the bursty behavior. Now, at the same time, so I think there is some evidence that it's not behavior that disappears as the resolution is increased. At the same time, I want to be cautious that the statement that I made is not equivalent to having demonstrated that the hydrodynamics is fully converged. And so, to me, there's a real question about kind of the apparent different mode of wind driving in simulations like yours and fire, and because I do not understand the nature of this difference, I want to be cautious about how the statement I want to make about this.
Well, we can take this offline. We will have plenty of time for interaction. Let's thank Claude-Andre for the wonderful talk.